one, and we are recording with Mr. Rob Manning, episode 210, author of Mars Curiosity. I'm already butchering it. Mars Curiosity Rover, the book about the Mars Curiosity Rover.
Yes,
USL.
And the book about Mars Curiosity. That's right.
I've now listened to it 3.5 times, and I've said this to other guests. I was like, normally when I have on a guest, I listen to their book a lot, and I can kind of, stumble my way through it. But this is literally like rocket science and space exploration. So this has been the steepest learning curve for me. So as I've said to everyone who does have an education in this, please be patient with me as I stumble through this interview. But I'm going to stop talking already. Mr. Manning, how about you introduce yourself?
Thanks, Tommy. Thank you for inviting me to come. It's really fun. I love sharing this stuff. I mean, I'm paid by all of you taxpayers. Thank you very much.
Happily.
For my salary. And I feel it's a real privilege to do what we do at JPL and in NASA. Mm-hmm. So I feel it's a good thing to share wherever we can, wherever opportunity we can. And the cool thing about Zoom and things like this or these other platforms is that it's much easier to do that. You know, it's not, I don't have to travel across country. I can just pop in and be there virtually with all of you and you, Tommy. So thank you. So my name is Rob Manning. I've been at JPL just under 40 years. JPL is the Jet Propulsion Laboratory. It's in Pasadena, California. It's one of the 10 NASA centers, and we specialize, and as we have since its inception back in 1958, for doing unmanned, uncrewed, it's the proper term today, missions that to explore outer space. Basically, we started with the first U.S. Spacecraft that was put out there after Sputnik was done by JPL in 1958. Oh yeah, I think early 58 or late 50. Roughly around there. And what happened was ever since then we've been sending missions out to look at the planets, telescopes, look at the sky. We turned our equipment back onto Earth, study Earth, the Moon, Mercury, the Sun, of course, Venus, Mars, all the outer planets, as much as we can. And so it's been really part of a wonderful adventure of opening doors, our understanding of our neighborhood, and Earth is part of a little neighborhood of these wonderful little planets and objects, and it's a very busy place. It's very exciting, and the more we learn about these places, the more we learn about our own world. So it's really not just strictly driven by just raw curiosity, which it is to a large extent, but it's also driven by our need to understand our own place in our universe. And so I think that's something that has driven me and my colleagues and friends who've been doing this for a long time, and who are very proud and privileged to be able to do this. So it's really a trip, and it's as cool as it sounds. I have to say, I feel I'm really blessed to be able to do this. This is my 12-year-old childhood dream come true, and here we are.
Yeah, and I remember when I emailed you, and this has happened a couple times now, where like I try to, I never start off on, here are episodes of me and my friends making stupid jokes that aren't worth anyone's time. I always lead off with, the more well-known guest. The one I always lead off with is Mike Durant, the quote-unquote Black Hawk Down guy.
Yes.
Your General Spaulding. I always lead off with those. And I remember when you emailed me back, you said, "I'm not sure if I'm as interesting as these guests. Why do you want to talk to me?"
Yeah.
And I remember thinking, I was like, I don't think I got the right guy's email, because I was like, there's no way this is. So I think I said in the same, lesser words as, "With all due respect, sir, you drive RC cars around with a range of 300 million miles.
Yes.
There's nothing cooler than that."
That's true. And I mean, I shouldn't say there's nothing cooler than that, but it is true that it's a real pleasure. And I think, and it's important, what interests people about this. And for me, it comes from, there's a engineering slant. There's an exploration slant. There's a science slant. You can come at it from all these different angles. there's a human slant to understand how, what does it take for humans to be able to do all this stuff? And there's a part about, how does this lead to, the possibility of humans exploring it in person? And so there's all the different angles to come at, and I'm willing to talk about all of them, but they are really interesting, and they're and there's a lot to it. My focus is I'm JPL's chief engineer. I've been involved in many missions, including before I worked on Mars stuff. I worked on missions to Saturn, Jupiter, Venus, and then I got involved in early on with first of all, my first Mars mission was Mars Pathfinder, which was our first attempt to land a little tiny rover and a lander. The rover is about this big. Her name was Sojourner Truth, Sojourner rover, and named after Sojourner Truth. And we proved to ourselves and the world that we knew how to land on Mars and explore a planet for the first time with wheels. Yeah. And so that really was a bit of an RC car, but unlike an RC car where you can control it, we've got a little problem in that Mars is as far as 20 minutes away, one-way light time. So and what's more, the power these radios require to talk is so great that we can't do it. In fact, the little rover didn't have a radio to talk to Earth. It had to talk to our lander, which had a radio and solar panels to talk to Earth. Yeah. And even that radio can only be on for a few hours a day. Otherwise, the battery would be discharged. So these vehicles had to be autonomous, robotic missions that followed high-level instructions in a script we would mail to them the morning they woke up.
Yes.
And so that's how we thought of it, and that's been the model that we've used for all of our missions that landed on Mars. So I did that. I was in charge of I was chief engineer for the lander, worked with the rover team, but also responsible for entry, descent, landing. And I kind of reprised a similar kind of role on Spirit and Opportunity rovers, and then I led chief engineer for Curiosity, and I've done other things in between. So it's been a real thrill. But now I'm chief engineer for the whole laboratory, which has many projects that are going on, not just Mars. Mm-hmm. We're developing a mission that's going to go around Jupiter, that's going to be swinging very close by multiple times to Europa, which is this little moon, very small moon. But this little tiny moon, we're almost 100% confident has 2 to 3 times as much water on that little moon than there is on all of our planet. How can that possibly be? The outside is like this hard shell of cracked ice, and that's very, very thick. We'd like to know how thick it is. And underneath that, there's this fantastic ocean that completely goes around the globe of this little world, and inside that is a rocky center. So it's a great place to go ice fishing, I suspect. We don't know. We would love to know, because this is so cool. Yeah. We can talk about this later, but I would love to point out that well, there's a sense that we are, especially at JPL, we are concerned. We study the Earth, we study the changes on our planet. We're able to look through the geological record and of time to look to see how the Earth has evolved with time. We've watched this planet change enormously, especially in the last 20 some years. We're monitoring things like, for example, the ice loss of Greenland and Antarctica from space. We're watching the changing climate and temperature. And there's a lot of changes going on here. Where we're worried about, how do these millions of species survive these changes? And so they're really concerned about extinction and things of that sort, because this is a big deal, very big deal. Mm-hmm. But we do know something. Historically, life survives. Individual species may not survive, but life itself is incredibly tenacious. It just hangs on there. If there is a will, there's a way. And if there's a way, life seems to have a will to make it happen. And so, and we're finding, for example, this massive, you might ask us, what do you think what area of this planet would you go to find the most life by weight?
By weight?
Yeah. Would you go to
I would say
the land masses, in the air?
I'd say Amazon rainforest soil
And
or thermal vents in oceans.
thermal vents and oceans. That's you're close. It turns out, and it's not fish. It's not all the whales and all the fish. It's not all the land animals. If you add up all the mass of all the animals on the surface of the earth, in the air, in the water, it probably does not add up to all the mass of life that lives below your feet and below the bottoms of the ocean, deep in underground in rock.
Really?
Did you? Yeah. So individual, we're talking about tiny microscopic organisms, right? Very tiny ones. You need a microscope to see them. But they're discovering that they're in huge amounts, and they're up to a kilometer below the surface. And since that air volume of space is so large, the total mass is unbelievably massive.
Yeah.
Life has, and how long has that life been there? Probably for hundreds of millions, billions of years, probably. And so we look at our planets. We look at we've studied the history of our own planet, as well as the other planets and how they evolved with the sun. And it's been really stunning. I mean, we all grew up together. All of us, all the planets grew up together 4 billion years ago or so, and that each because they were interacting, they were bumping into each other. There was we believe a Mars-sized planet slammed into Earth. You may have heard about that. So we went around then. Thankfully, it would have been a bad day, and created this incredible massive debris, which mostly made up of Earth stuff thrown up into space, because the Mars-sized object went into the Earth. and leading to a giant molten ring of rock. Imagine a molten ring, glowing hot ring of rock that's out in space, which finally coalesced into our moon. And so our moon, one of the shocks that we had when we sent astronauts and brought back rocks from the moon, was that, wow, these rocks have the same elemental composition spectrum of Earth rock. What are the odds of that? How weird. And so over time, we realized that in some sense, Earth has been blessed by having this moon, because it's kept our planet active. The plate tectonics, the motions of the continents moving, the subduction, taking trillions of tons of plankton shells back, that pull carbon out of the air, drop them down to the bottom of the ocean. They get subducted, pulled down into the Earth, rotates, and gets shot back out again on volcanoes over a course of millions of years. And so and then we have the moon to thank for that.
Yeah.
And so we're a very lucky little planet to have this. In fact, if you lived in another solar system and looked back and you had a telescope and you looked back at Earth, you wouldn't say there's Earth here. You would say there's a binary planet.
Yes.
Right. There's two of us right next to the moon and the Earth, because the moon is pretty big. So we're a very lucky place. And so the question is, so first of all, what was going on about then? That was very early on, but the not long after that, Mars was starting to get its act together and was starting to get a little bit more. It was cooling after the initial bombardment. It was cooling down, and so there's a really good possibility that Mars had this conditions very analogous, because it had water. We now have evidence from our orbiters and landers and rovers that Mars was once indeed a wet, warm place. So maybe life existed. Maybe life got started on Mars the same time they got started here. If not, why not?
Yeah.
And so how single cell organisms were born, how they were where they find places that are safe to live, is something we study. And in particular, especially when we go to Mars, we asked ourselves, where would we find life if we looked for it there? And certainly the surface of Mars turns out to be a very inhospitable place, because the Mars does not have a moon. So it doesn't have internal plate tectonics, which means it doesn't have a magnetic field of any substance, which means that magnetic field, which acts as a force field, like we have on this planet, to deflect these particles from the sun, right? These particles charged particles from the sun and from galactic cosmic rays come streaming at our little planet, and they hit our magnetic field and they start curling. Mm-hmm. They do this QV cross B kind of a thing, action, where they just basically coil themselves up, and as the field lines get tighter and tighter, they turn around and they take off in the other direction, so they never make it to the surface. So we are protected with this really cool force field. Thank you, Mr. Moon.
Thank you, Moon.
And on top of that, because we have life on this planet, we have oxygen. Mm-hmm. And because we have oxygen, the oxygen raises to the upper atmosphere, interacts with the ultraviolet light from the sun, and it converts that oxygen from O2 into O3, which is ozone. Mm-hmm. And although we don't like ozone down in our cities, because it's not good for our lungs, it's very reactive, it's very good at blocking ultraviolet light. So we have a little shell, we have some sunglasses that go all around the planet called ozone, which is like a pair of decent UV sunglasses that knock the UV radiation down. So now life on this planet is like, hey, we're protected from these bombarding particles from the sun. We're protected from harmful ultraviolet light from the ozone. This is a great place to live. It's like, someone built this little house for us. This is nice. And no, that didn't happen on Mars. At least not anymore. There's never, as far as we know, there's never been oxygen. We don't know for sure, but it doesn't appear to be sufficient oxygen to produce ozone layer. But it doesn't mean that life couldn't form underground. And so, because the underground can make similar kinds of protections for organisms to live and thrive away from the harmful ultraviolet light and the cosmic rays and solar particles that stream onto the surface. Yeah. So ask yourself, so maybe Mars. So Mars is a wet world when Earth was actually kind of still getting its act together. Maybe life got started there. Another thing we've learned is that life can travel back and forth. Mm-hmm. That's kind of interesting. How could that? We don't know. We've never caught life in the act of doing that. Yeah. So we don't know. But though we do know one thing. We do know that Earth rock has been to Mars, and Mars rock has certainly been to Earth. In fact, we've got plenty of it. Mm-hmm. Not plenty of it, but if you happen to find one, keep it. It's pretty. You might want to donate it to a researcher, though they're pretty expensive on eBay. But the Mars rocks have landed on Earth. They got off of Mars because a large meteor impact hits Mars. It threw into space. That rock floats around in this orbit around the sun for a few million years until it bumps into Earth, and then lands on Earth, and for someone to come back and pick it up later. And so we've found rocks that are guaranteed to be from Mars, and we know that because when you open these rocks up and sniff the gas that's inside, that gas has the same fraction of atoms that's unique to Mars's atmosphere, and the kind of atoms, basically the isotopes of carbon and oxygen, carbon dioxide, which is trapped inside the rock itself. So we know they're from Mars. So it turns out Mars and Earth are pretty close together, and there's a little freeway. It goes back and forth, sending these little rocks back and forth, and these little single organisms are hitching a ride. The question is, when they land, do they find a nice hotel to stay at? Yeah. We don't really know whether they can survive once they get there. We think they can survive the landing, which is pretty rough, gets pretty hot, but the outer shell, but the inside stays relatively cool, doesn't quite cook them. And so, maybe so. And maybe Earth life has seeded, for example, all the planets, including Europa. Yeah. Now if we go there and we find Earth-like life in terms of its DNA structure, its chirality, the handedness of the molecules, right? Yeah. And we find that we have to ask ourselves, is that something that nature just does and it happened to happen in parallel? Or did Earth life travel there, or did life travel from there to here? Maybe we're not terrestrial. Maybe we're Martians. I think that'd be kind of cool.
Or
I
maybe
do
we're
feel
solar.
sometimes I feel like a Martian sometimes.
That's the most interesting part of your book is beginning. You say, did we seed Mars or did Mars seed us? And it's
Exactly.
is that just because it starts to get, was that really Mars life if it comes from Earth? But that might be as natural a process as, you know, uh, you know, plants blowing their seeds into the wind. It might be that natural.
Yes. And so this idea of things moving around is called panspermia.
Mm-hmm.
I'm skeptical that it goes clear across in between planets, between solar systems. So, but I do think that there is a natural, I think it's not hard for life to get started as we think it is. Or doesn't take us not that much time to get started. You need a lot of conditions to maintain it, to keep it going for billions of years, and having a moon doesn't hurt.
Mm-hmm.
But because of all these discoveries, I'm understanding about the ubiquity of life, the tenacity of life, the structure of life, the diversity of habitats for places to live out there, and the discovery of planets around other solar systems.
Mm-hmm.
It's really stunning that our view, the scientific view now, that is that we really are, life is probably ubiquitous out there.
Yeah.
When we say life, we don't necessarily mean
Possible thoughts.
yeah.
Yeah.
Exactly. We don't necessarily mean people we can talk to.
Sure.
In fact, it's complex life forms. It's kind of, it seems like derogatory to say this, but it's not. Our bodies are giant walking colonies of cells.
Yeah. Yeah.
Right. We each one of us.
Yeah.
And we think of ourselves as a unity, as a single us.
I'm me. No,
I'm me.
Your butt.
Right. But we are really this coordinated colony of cells that are trying to keep going, trying to reproduce themselves, trying to survive, in order to maintain the incredible pattern of survival that life has established over billions of years ago. And we have this wonderful brain that has constructed, it helps construct a worldview that puts us as an object in its mind's eye, and allows us to see the world and make models of the world in our heads, to see things, just to try to make sense of the world so we can survive. And so we're very good at it, but that particular model may not be that common.
Yeah.
It may be something much simple. I do think that multicellular smart colonies are not uncommon, mm-hmm. but whether or not that they'd create internets and social networks and Zoom and or other
podcasts,
yes, or spacecraft of their own.
Yeah.
That's a different matter. And so I think and it may not last. Those things may not last very long. It's not clear that us as a stable species is in the cards. We seem to be very good at gobbling up nature's resources. And we were so lucky, a couple hundred years ago, to discover this incredible reservoir of energy that's just had our name on it. A gift from God, right there underground with our name on it. It's just for us. We just pump it out of the ground, refine it, put it in our cars, and off we go. Yes. And so we're, unfortunately, we're using it up very quickly, and it's having some adverse consequences. But anyway, so those are that's the world I live in, so but my job really is just to make the machines work, make us succeed at getting to the science, be able to reach in and learn these things about our world. And it's a real thrill to be part of this massive team of people who can pull these things off. They can actually, it's because there's, we like to say, well, people say, oh, Rob, you're a rocket scientist. I know, no, there's no such thing as a rocket scientist. All we are is just a bunch of people who learn various little disciplines, mm-hmm. and we team up to see if we can put our different skills together and see if we can build something. that might work, and hope, cross our fingers that we didn't screw up. You know, you've seen us on like landing day, we're all screaming up and down. And I see, probably noticed in my book that, you know, the real, you know,
90.9, not that.
That's not happiness.
It's
You're seeing it's deep relief that we didn't make a mistake.
We did it.
And
So
because humanity, humans are really good at making mistakes. We barely know what we're doing most of the time. I mean, but we struggle. And the great thing about things like science and engineering, we developed it's the best human pattern that we have developed so far.
Yeah.
That helps us get over our own weaknesses and shortcomings. In that we have to acknowledge our personal and human fallibilities in order to pull these things off. And so you've got to be humble while you're being bold and audacious at the same time.
It's like you said in your book, you know, to even, you know, you got to be pretty arrogant to even believe you can land on another planet.
You too, or an idiot.
Yeah. Hey. Fine line.
I think I have to. I've been at JPL something like 13, 14 years when I started Pathfinder, and it was more like, you guys think we could do this?
I don't know.
They
give us money? What the heck?
We kept doing like the math. I was like,
close the door.
This math seems to show that we can do it. Do you think we can?
It's like winning the lottery. There's no way.
There's no numbers. But then we build it and test it. Now over time, it's like, you know, I think we'll get this to work. What do you think? Yeah, I think it's going to work.
That's crazy.
How about you? What do you think? Do you think it's going to work? I think it's going to work. Yeah. So over time, you start like, you know what? I guess I get. And it's really not about getting it to work.
Yes.
It's getting it to not fail.
Yeah.
Two different things, it turns out. When you think about not failing, you spend all your time thinking about why it won't work. And if you knock one of those off one by one, like a little machete, you knock that one out. I think that one. Oh, there's another one. Gotta get that. Once you've seen all those little goblins are knocked down, then you just discover that you're there.
Wow.
And because you can't focus on how it goes right. You have to do that a little bit. Oh, I'm sorry.
You're quite all right.
I'll stop here a second.
No, you're good.
Can we pause?
Yeah. I can cut this out. Take your time. Yeah, I'll mute it. You can go take a call.
Nope.
Okay.
We got it.
Okay.
You can resume.
Okay. That's beautiful. It's not it's just you keep knocking away all the others until
all that's left standing is the thing that works. And you have to do that because there are so many ways. I mean, think about, thinking about Curiosity landing on Mars. It's got like 79 pyrotechnic events. These are individual explosives. They're very small. They bang, they explode, creates a little pressure increase that usually pushes a piston, which causes something to happen. Often, for example, it will push and cause a nut on a bolt to break open, or a guillotine to come along and cut metal or even electrical cables. I think your mom probably told you not to play with knives around the electrical cables. Like, don't do that. So we have to be careful when we cut our cables, by the way. I mean, but there's all these things that could go wrong. People, my teammates and I developed this sky crane idea after the airbag bouncing landings, and it was not like, oh, here's the best solution. No, it was the least unsatisfactory way to land a rover of that size. You have to kind of like turn it around. Like, oh, that doesn't sound like a big, the least unsatisfactory. That sounds like you're knocking it, but no, there are no perfect ways and foolproof ways to do anything, especially since we've only been exploring these planets for a relatively small number of years. in the grand scheme of things. And there's not been that many missions to the surface of Mars. And most of them have some patterns, and we've gotten actually good at it. To be honest with you, we're better at, I'll knock on wood. I shouldn't say that because we got one mission on its way to Mars right now. And I think that we've got good at the pattern of what we need to do. Whether or not that's necessary, I mean, I believe that's necessary, but whether that's sufficient to assure a safe landing of a billions of dollar mission, $2 billion mission, is, I think, I have no idea. I mean, people ask me, Rob, what's the probability of landing? And I go, I don't know. None of us do. All we know is that we can't find a reason, which we already spent all our time trying to find reasons why it won't work, and try to fix those. Mm-hmm. What's left, again, is unknown as to whether or not we're good enough as human beings to foresee all possible outcomes, and including our own shortcomings, our own mistakes. All it takes is one case where somebody over-torqued a connector, a bolt, mm-hmm. or nut, and they didn't know they'd breaking the bolt, and the bolt's sitting there right now, broken in space. And as soon as we get there, the parachute's going to fall off, something like that when the parachute inflates. And so, no, who knows?
Yeah, that's such an odd. Yeah, I never would have thought of that. That's actually a parallel to what surprised me the most about, not to go back to it, was Mike Durant in his book about being captured. Is the thing that stuck out to me was, in my mind, I was thinking he's part of the 160th SOAR, which is like the special forces of helicopters. And I'm like, oh, this is, focus on success, don't lose the light. He said that the only thing that got him through it was focusing on failure, was acknowledging that he'll never see his family again. And because of that, he couldn't let himself down. And that blew my mind. And it's kind of, in a weird way, it's what you're saying. Like, it's not that we choose the thing that works. I mean, it's natural selection. We just kill off everything that doesn't work. And finally, the giraffe might not be the best, but hey, it's the one that's still here. And it's, it's our beacon of Finch, right? Galapagos Islands. It's
exactly. It's whatever. And it's whatever makes it work. Yeah. And I think that's something that we have to recognize as human beings, is that it takes a lot of work to get things to work.
Yeah.
And when we focus on destructive activity where we tear things down because we don't like it, or it's just, the amount of energy and time people put into make things happen. So what's so great about being an engineer is that you're paid to construct a better something.
Yes.
At least hopefully. Not everyone's paid to do that. Of course, some people are just paid to destroy, or for defense. Uh-huh. But I definitely think that the bulk of engineering is about trying to make something better. Sometimes better is defined as making more profit for the shareholder. Yeah. But we're very lucky at JPL that you are our shareholders. Yeah. And we're trying to put ourselves in the context of our world and our universe, and to understand the context and learn about us. I mean, think about this. We learned, it was I don't know if you know this, back in the 1980s, we were developing the Venus Orbital, VOIR. It's the Venus Orbiter. I can't remember the acronym, but it was a spacecraft to look at, to put a radar around Venus to see what was underneath that big cloud deck. So Venus has got this massively thick cloud deck that the bottom of that thick atmosphere is 90 times the pressure of our Earth atmosphere. If that atmosphere has got, and what's more, upper layers of the atmosphere is got sulfuric acid floating in the atmosphere. Yeah. It's not a great place to hang out.
Yeah.
By the way, it will melt tin on the surface. So you land a vehicle there, it won't last long before it melts. So it's a terrible place to go. But we wanted to find out more about it by mapping the surface. So we sent a radar around it. And in the process of doing that, we were studying it, and we were trying to understand, first of all, we were trying to understand, why is it so hot? Why, it's closer to the sun, but that's not the whole reason. It turns out sunlight goes inside and doesn't bounce back out again. And we said, oh, that's just like a greenhouse. We should call that the greenhouse effect. Mm-hmm. Yeah. And so, of course, that wouldn't happen on Earth.
Yeah. Yeah.
Would it?
Nudge, nudge.
No. It says, oh, that couldn't happen. We don't have greenhouse gases like that. And then we discovered later on that was not quite true. But in the process of studying Venus, we learned that. At the same time, so we sent this vehicle around and got this wonderful global map of this whole topology. We saw the mountains, volcanoes, right through the clouds. We saw the whole planet. And people said, wow, that's fantastic. How does it compare with Earth's global map? There is no global map at that time. Like, no, we've done it for Venus, but we've not done it for planet Earth yet.
I didn't know that.
And people said, what?
We mapped Venus before Earth?
Correct. And so many years later, so by a decade. And so our people in Congress and said, wait a sec, how come we don't do this for Earth? And says, well, we're not paid to do it for Earth. We're paid to do it to Venus. And they said, well, maybe you guys should do it for Earth.
Yeah.
And so, because up to that point, the topographic maps we'd done had been measured by some of that with aircraft, but a lot of it mostly was done by surveyors with metal tape and with basically large tape measures. And they would actually measure things and heights, and they used theodolites to look up and measure angles and get all the shapes. And so those USGS topographic maps were made by combination of aircraft, stereo imagery, and people measuring. But that didn't cover the whole planet, but hardly, because that's a very, very labor-intensive effort. So when we finally they said, let's just do the whole planet at sub-meter resolution. Let's do it. So we put a massive antenna inside the belly of the space shuttle and put a big boom out there where the transmit antenna, receiver antenna, a big flat piece of metal, a receiving antenna, and fly it upside down and fly it over Earth for a couple of weeks and see if we can map Earth. And we did. And it took, so this radar mapping system, it took us about a year or two to process all that data at JPL that we collected over a 2-week mission in 2002. And within a year, right by 2003, 2004, we were able to put out to the world a full digital 3-dimensional map, which became the basis for Google Earth, for example. So now since then, it's been improved enormously through other means, other satellites and other things. So the resolution's gotten better and better and better. But up until that point, there had never been a satellite-based global topographic map of the planet. But it's only because of our exploration of of Venus, that allowed us to see that we developed for planetary work, that we realized that we could bump it back and say, hey, this planet could use this too. Pilots could use it. Now you integrate that information with GPS. Now you have smart train avoidance systems on aircraft.
Yeah.
It's completely changed the globe. It's really, there were parts of Earth that were, still left in the map up into even to 2000 that said unexplored territory. We don't know what the shape of the Earth is here. Literally, because no one had looked at it yet. There are places there in South America, Himalayas, and parts of China. There are parts of the even some parts of Canada and the United States. So that really had not been mapped because it's just, there's just too much area. But doing it from space in this very global way with a very powerful radar made all the difference. So we do things like that. So I'm not at all talking about the questions you sent me, by the way. I'm sorry.
No. Hey, questions are suggestions, and they're suggested. What's the word? Scaffolding. That's what I do.
Scaffolding. Sure.
Suggestive scaffolding.
So
Now,
since we don't have a lot of time left, you should throw me some questions so I don't dominate.
Oh no, dude, this has been so perfect, because sometimes, more times than not, it is like pulling teeth. You show up with perfect audio and fill in the conversation. This is the best. This is the new gold standard for what.
Oh, great. Well, thank you.
It is. So you're not dominating. You are in the best possible way.
Do you think, or your audience, do you think there are things that they'd be interested in hearing? I've touched on a lot of different areas, but I can talk a little bit more about what we're doing now. I can talk more about how rovers on Mars. We're going to say something about how what we're learning about Mars could have an impact on future missions to Mars. I know NASA's working right now on a competitive selection between various companies who were trying to build a lunar lander on the moon, and by 2024 timeframe. And it's a really huge effort going on all around the country right now. It's a big effort to build these things. And but there's then of course Elon Musk and his organizations, and as well as Blue Origins and others are trying to look at, how do we extend this technology to taking it to Mars, and so that human beings can actually set foot and explore Mars. And so it's a real challenge. There's a lot of things ahead. I mean, I think one of the challenges we have, one of the downsides of this COVID-19 event, is that our financial wherewithal to fund discretionary things like this is going to be put off for a few years, I'm afraid. I think our budget has been eaten into a lot by the cost of this event. But that aside, I still think all the technical roadblocks for going to Mars and for two-way flight. And I recommend two-way.
Bringing back both.
People were talking for a while, we're just going to one-way trip. And I go like, and then what? Well, we'll just live there. I go, on what? There's no trees. It's not like you can send them across the Atlantic Ocean from Europe and survive in the woods with a little help from the Native Americans.
Live off the land.
And live off the land. There's nothing to live off of. There's water underground you can dig up in various parts of Mars, which is great, by the way. That's big news. That's something. But one of the biggest problem of Mars is that there's no electricity, and there's no trees to burn or coal, and so you have to bring either solar power with you or nuclear power with you. And we have not yet developed the technology for large nuclear power supplies and reactors to send to Mars. And that would help. Now, solar panels work fine, except, as we learned, I don't know if you remember, Opportunity rover died a couple of years ago.
With the dust all over it, right?
Well, the thing is, it's more than just, there was dust, but that's not the reason it died. It wasn't the dust that landed on it. It's just that somebody turned off the lights. The dust storm was so dark. So if you were there at Mars, you would need a flashlight to walk around. The sky was pitch black. It's those pictures, those surreal pictures of parts of California with these dark fires. It looked a lot like that, with just night in the middle of the day. And that was true. Unfortunately, that lasted for many, many weeks. And so even if the solar panels were perfectly clean, the light wouldn't be coming in. So if you were on Mars during that kind of an event and only had solar power, you might be in some deep trouble. Or you might have some big battery packs and fuel cells for emergency use, but you'd have to hunker down for weeks and weeks until the sky started to clear again. So, but those are rare, fortunately.
Do you think that, I've brought this up before, and I got you for 5 more minutes. Don't let me keep you, because I will keep you hostage. I keep verbal hostages. I'm terrible.
Okay.
I'll try to be good. Do you think that it kind of seems like, I'm a big Elon Musk fan. I'm also a Jeff Bezos fan. I don't think there's a need to choose between the two. But with Elon Musk, isn't it kind of weird that he also has the Boring Company, right? And everyone's, he just wants to alleviate traffic in LA. To me, that seems like he's just trying it out here to see if we can work on Mars. Why not master the technology?
I think he's actually, he is a bit of a visionary. I've actually worked with him a bit in the past, even before SpaceX. Really? And he's very, he's incredibly driven. His self-confidence is through the roof. This guy's amazing. Yes. I wish I had that kind of self-confidence. But he is and he's brilliant. He's a brilliant thinker. Yes. But he does see that, he wants to get from his house to Hawthorne, California, where they work, where the SpaceX is. He doesn't want to have to get a helicopter. He doesn't want to have to wait in traffic. He actually wants our world to be efficient, and and he wants our problems on this problem to be solved so that he can
We
have
can.
Earth move, have people coming back and forth from Earth to Mars. If Earth falls apart
There's
because we haven't been taking care of it, his vision for going to Mars is going to die with it, because we need Earth to be a strong home base.
Yes.
For wherever we go. And so that if we don't take care of this little planet of ours,
Nothing else is gonna work.
we're in deep trouble. So, and he has been, with Tesla, his battery banks, his ideas, the solar cells, the wonderful solar cell designs that people are working on for him, for that looks like roof tile. He's trying to make it so that our world can be self-sufficient. And I appreciate that from him. But I think it's all part of a strategy to make sure that, well, and not just to get to Mars, but to be a spacefaring civilization, and to take the civilization to another place.
Yes.
But we definitely have to start working together, though. I mean, this is something that's really scary to me, is that we've, the more we are yelling at each other,
it's
the more the less we talk, the more realization there are no bad guys. The people are just trying to live their lives.
Slight disagreements,
and the thing is, that's how solving problems is by working together. I mean, there's nothing we do that we do at JPL which is that you can say one person told everyone what to do. Now, there's no one in charge. Somebody has to be a buck stop here person for making ultimate decisions and flipping the big coin. When time makes, we have to choose path A or path B. We've got all the information. We've got all the pros and cons for each of them. Everyone's got to set their vote in. It's okay. I'm going to flip the coin and we're going to B.
Yeah.
And fine.
Got to commit.
And you need that. And to make forward progress, you've got to be able to make baseline decisions. But we need people for this to work. You'd have to work together as a team. You have to listen to everybody, and you have to listen to small voices and big voices. It's not just the loud people. It's not just the people who so everybody brings something to the table. There's nobody who doesn't know something. There's nobody there's nobody that doesn't know something that you already know. I'm not saying that right.
No, I know you're saying
everyone knows something. Everybody knows something that you don't know.
That everyone has their own unique piece of the puzzle.
Right. And everyone knows something that you don't know. And you have to be respectful and quiet enough to listen to them. And so this is something that is so fundamental to the work that we do at JPL.
Yeah.
So fundamental for successful engineering, getting groups of people with all this diverse skills, with all these diverse backgrounds, from people from every country in the world to work together to make something extraordinary happen.
Yeah.
And for us as Americans to be extraordinary and to continue to be an amazing place, we have to fall in love with that idea.
Yes.
We have to fall in love with listening and working together. Yeah. And getting our hands dirty, rolling up our sleeves and getting out there.
Yeah.
And
arguing is good. Yeah. Arguing is good. You talk about it you'd say you guys went to the retreat. Everyone be quiet and you go around. No writing down, no scoffing. You say your ideas. And once you go around the circle, you do it a second time and then a third time. And people leave with, oh my God, the feeling of I'm being listened to. We need to do that now. We need to do that now.
That's right. And you don't have to agree with the decisions ultimately, but you have to, if you know that your ideas are understood and acknowledged, and the risks, particularly the risks associated with not understanding what they're doing, are well understood and acknowledged. People are willing to go with those ideas and says, okay, they understand what I'm talking about. They acknowledge it and they're respectful of the idea. Yeah. But I think this is so essential for humanity working together to solve problems. And so I'm very, one of the things that's so wonderful about my job is I get to work with this incredible diversity of people from all over, not just in JPL, not just in NASA, but all over the aerospace world, even outside the United States. Where our goals are to be successful and work together and acknowledge that we need each other to succeed. Yes. And that's so cool because we actually do it.
Yes.
I mean, this is not something, these are not just conceptual ideas. This is actually something that happens. And what results in is this amazing missions where you land, in our case, collecting samples to be brought back to Earth, which is what the next mission on Mars is going to do. It's going to collect samples and drop them off on the surface of Mars for a mission called Mars Science Sample Return, which will come in and grab it. Another rover is going to pick it up, put them in a rocket and nose cone, launch that rocket into outer space. That nose, a little ball about the size of a basketball with 30 some samples in it, are going to be rotating around Mars for a number of years. And another spacecraft, like from now looking at a European spacecraft, going to come up, gobble it up, and an American space capsule is attached to that, and it's going to drop it off in Utah in the early 1930s. And so this is a sample return mission, and it's something we're doing very soon, and we're making this happen.
It's 2:02. I said I would let you go at 2. I could talk to you forever. Rob Manning, yeah. I hope I can get you back on here for a part 2, because I love to hear you talk.
Oh, you're welcome. Well, I have a lot to say. So it's a lot of cool things. So I need to run.
Yes, sir.
I've got another meeting, but we'll schedule something in a few months.
Yes, sir.
Yes, sir. Some weeks. So
I'll email. Hey, you tell me what day, and it will happen.
Okay.
You want it next week or in February? You tell me.
Okay.
It'll happen.
How about we do this toward the end of the year?
Towards the end of the year?
Yeah.
Yes, sir. It is my podcast.
Okay.
Your podcast.
All right.
Thank you so much, Mr. Manning. Thank you so much. God bless.
You're welcome, sir.
And I will happily pay your salary for the rest of my life. Doing God's work. Thank you, sir.
Thanks. Take care.
Good one.
Bye, Tony.
Bye-bye.